Everybody, welcome back to another fun and exciting geometry class. Today we are going to be doing kind of two lessons into one. If you're in my class, then you just took a test, but like I've told you before, this book is kind of just spaced out a little differently than a lot of books, so we're not changing chapters or anything. We're just kind of continuing on with where we were, and we're in lesson 2.5 in your book, and that's on page 57. Lesson 2.5, page 57. Today we are going to be doing triangles again, and we are going to be proving congruency again. And today's lesson we're going to be proving congruency with side, 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 SSS. When you prove with side, 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 here's kind of what it's saying. What it's saying there is you have proved, instead of using any angles, you've just proven all three sides are equal. If you can prove that all three sides are equal, then you have also proven that all three angles are equal. And when you do that, you have congruency. Now, let's talk about that for just a second. So if I just drew two triangles on there quickly, just like magic, they appeared. But if I draw two triangles there, and they are congruent, I just copied them, okay? I just drew one and copied the other. And if I can prove that this side equals this side, and I can prove that this side equals this side, and then this third side is equal to this third side, I have proven that those are congruent. In other words, you cannot take three equal parts, three equal pieces. Like I can't take this piece, and this piece. Remember, those are like equal parts. I can't take those three equal parts and make them a triangle by putting them together in any other way than this right here. It will make a congruent triangle. In other words, the pieces, because of the length, they don't fit together in any other way. You cannot close the triangle. You cannot get the triangle to be closed shape in any other way than what is congruent to the first triangle. When all three sides are equal, the triangles are congruent. That's on page 57. One thing that I've been telling you kind of all along is that I am not going to do every single proof that's in your book. There is a proof in your book on page 57 and page 58 that proves that. I'll go through it, I'll talk through it, but I will not be doing every single piece of it. The way that you get this is by basically taking that triangle and mirroring that triangle down here like this. Okay? And what you would do is you would take this and cut this right here, and you can see it in your book. And you take and you make two triangles there, and then you have a definition of an isosceles triangle in there, and you just keep going through the proof. This is how Euclid proved it, okay? And what you end up coming up with is then you're proving the angles to be equal because it's isosceles. And once you prove the opposite angles are equal, then you kind of have side, angle, side. And then if you have side, angle, side, then they are all congruent. It's kind of a long proof, but here's the idea. The idea is this. Once we learn it, once Euclid proves it to us in the book, then we can use it. So let's go back to here. I'll take that off. Every time when you're trying to prove a triangle, now you have three ways to prove it. You have side, side, side. You have side, angle, side. And you have angle, side, angle. Okay? Those are your three ways to prove. And those are the only three ways to prove congruency. Okay? Angle, angle, angle does not work. Okay? If you think about that. Angle, angle, angle. Well, that should work. No, because you could have two triangles that are very similar. So those angles are all the same as these angles. But the sides are bigger. So angle, angle, angle doesn't work. They give you what's called similar triangles, but they don't give you congruent triangles. So angle, angle, angle doesn't work. And there's other ones that don't work. Remember, you always have to, this is another key right here, that these have to be in the right order, okay? So you can't have these things out of order. In other words, you can't have, I'm going to do it, okay? You know what I'm going to do. I'm going to do it. You cannot have, sorry, I thought I was going to do it and then it wouldn't let me. You cannot have angle, side, side. And I'm doing it for a reason, okay? Because I want you to see you can't have it if it's out of order. In other words, that's this one right here. That's side, angle, side. But the angle has to be in the middle. It has to be the included angle. This one will not work for multiple reasons, okay? It doesn't work because the angle is not the included angle. In other words, you could have two sides that are the same, but if one of the angles on the outside is the same, you could have a different shaped triangle. The included angle is the one that has to be the same. So be careful that you are making sure that you are using the included angle for this one and the included side for this one. So you can't have an angle and then a side outside. So AAS doesn't work either. Angle, angle, side doesn't work. So be careful that you are including the piece in the middle. The adjacent piece has to go in the middle. That's what's helping you prove congruency. Okay. Let's see what else here. I think that's about all that I need to teach you from that lesson. That was a quick lesson because you've already gone through the other two and you already kind of understand the concept of congruency there. All right, page number 59. Page 59 is 2.6. The relationship between an exterior angle and the opposite interior. So now we're not working with a congruent triangle anymore. We're working with just one triangle. All right, so there we go. There's one triangle. Now this just happens to be an isosceles triangle. Doesn't have to be an isosceles triangle, but this one is. Because that's what my program draws, is isosceles triangles, unless I draw it. So here's what they're saying. If I take one of these lines, and it doesn't matter which one, I'll just extend this one. Now let me label this guy. This guy is, we'll call it A, B, C. Actually, your book calls it, I think this one calls it B. And then we'll call this, actually we'll call the inside B, and we'll call the outside one D. Okay? Now, this is the outside angle that we're talking about, the exterior. Okay? This would be the interior. This would be the exterior. What this theorem is saying, theorem 5, an exterior angle of a triangle, so this one right here, is greater, it has to be greater than either one of these, the two interiors. So in other words, the exterior of B, the outside of B, or angle D we'll call it, is greater than either one of the other two. Now I drew, the one I drew hopefully is an exaggerated example so you can, it's obvious to you. In other words, angle D is greater than C. It has to be. And D is greater than A. It has to be. That's what theorem number 5 is telling us. Now here's the question. Why? Why is it bigger? Well, let's logically talk about that for a second, and then you can look at the way Euclid proved it. Euclid proved it a little differently than I would. He proved it purely geometrical. I'm going to prove it a little bit more logically and maybe even with some algebra. So it doesn't matter how you prove this. What matters is now that it is proved, now we can use it. So we'll kind of do some thinking through this one. All right, how are we going to prove this? Well, here's what I want to base it on. The idea of 180 degrees. A plus C plus B equals 180 degrees. It has to. That's our first. That's the triangle equals 180 degrees. Now watch this. This right here is a straight line. So B plus D also equals 180 degrees. So let's do a little substitution here. Let's do a little kind of just messing and moving of these things. A plus C must equal what? They equal B. Okay? Because if we have B in both of these spots, then we have to have AC equals D. And we can do that with numbers. Let's pop some numbers into these. Let's say that A is, and I'll try to use some numbers that make a little bit of sense. So we'll say that A is, let's do 80 degrees. C is 80 degrees, and B is, that would be 20 degrees. So those make sense. So if we say, if we know that B is 20 degrees, and we know that this is a straight line, then what is D? D has to equal, okay, because this is 180. So D would have to equal 160. D equals 160. All right, so there's our numbers that we've put in there. And so now look what happens when we put our numbers in there. So 80 plus 80 plus 20 equals 180. It does. And over here, we say 20 plus 160 equals 180. Now, what we're going to do here is let's put in our numbers. So 80 plus 80 equals 160. Is that true? It is true. And so I'm using logic, and I'm using kind of substitution, and I'm using some algebra in there to say that there is no way, if you have to have two of these. Now, it doesn't even matter what those are. They're equal in this case, but it doesn't matter if they're equal or not. C has to have some value. So let's plug different numbers in there. Let's plug some random numbers in there. Just make something up as crazy as we can make it. So let's say D is 120 degrees. Let's just say that A is 119 degrees. Well, C has to equal 1 degree. You have to, I mean, in order to have a triangle, it has to have 3 angles. So C has to have some sort of a degree to it. So if you'll notice something here, this D always has to be bigger than either one of these. Now together they're equal, but because there's 2 angles that are interior angles, okay, since there's 2 angles here, the parts are always going to be less than the whole. The whole is always greater. What's the whole? The D is the whole. And so the parts, the pieces, are always going to be smaller. The whole has to be bigger than the 2 parts, okay? And so the 2 parts, when you add them, equal the whole, but they're smaller. Hopefully you followed that. If not, then there's maybe another way that you can follow it, and that is through looking at the proof in the book on page number 60. I'm not going to do the proof, but the idea of the proof is that Euclid first proved side angle side. He first divided them and turned it into side angle side, or in other words, he proved that you had a side, an included angle, and another side, And then he said, okay, if I have that, if I can get it into side angle side, then I can prove that the corresponding parts are equal. So angle C equals angle B in his proof. And then the exterior, and he basically went around the triangle. Very complicated proof. Okay, if you're looking at it and if you're going through, it's a very complicated proof. So maybe what I showed you here on the screen made a little bit more sense to you. And you're like, okay, well, that makes sense because they have to basically here A and C plus B equals 180 and B plus D, so A plus C has to equal D. They have to be the same. And if I have them the same, then the two parts have to be smaller separately. Each part is smaller than the whole, which is D. All right, so lots of stuff going on there. Hopefully you understood at least some of that. There is one more thing that I need you to look at, and that's on page 60, and that is Corollary 5.1. And Corollary 5.1 says that one and only one perpendicular can be drawn to a line from a point outside the line. So if we have a line, it is saying that if I have a point outside of the line, so there's a point right there, I can only draw one perpendicular line through that point. All other lines that I try to draw through that point are not going to be perpendicular. I can draw any other line through that point and it will not be perpendicular to the line. I can only draw one perpendicular line through the point. Now, you say, why is that a corollary of this theorem? Well, again, using Euclid's logic, that made sense for him to do this. And there's reasons why. Because if you look right here, I am forming a triangle. And that triangle uses, what he used was he used these exterior angles up here to prove that point. But again, I'm not going to go through and show you how he proved that corollary. But now that he's proven the corollary, now we can use the corollary. So what is it? One and only one perpendicular line can be drawn to a line from a point outside. We've already done the construction, and now here is just kind of the next logical point from that. And that is, I can only draw one perpendicular line. That's it. Now, I could put another line somewhere else. I could put another dot somewhere else and draw more, but only from that point and to that line, I can only draw one perpendicular line. That's Corollary 5.1. Okay. Alrighty, that's it. That's all I got for you. We'll see you later. Bye-bye.